Dev. Super. Okay, when I look at the clock, it's 8:45 on a Wednesday, May 12th. Welcome to the 9th lecture on multibody dynamics. Today's topic is going to be the Newton-Euler equations of motion for a 3D rigid body. So finally we are going to move out from 2D to 3D, and I always tend to say that strange things happen out there. So it's really that for the planar dynamics things are what you expected, but as soon as you go out in space, motion of three-dimensional rigid bodies in this case, even simpler, sometimes very surprising things will happen, and hopefully we will address that today. Okay, so we want to know with our Newton-Euler equations of motion, we want to go from the two-dimensional case to the three-dimensional case. And to do that, we first do a recap, of course, what was it in 2D? So let's remember, how did that go? Well, we had some inertial frame, right? And with some coordinates, an ordinate and a coordinate, and then there is for a point mass, what could we write there? We say, well, okay, the sum of the forces in the x is the mass times the acceleration in x. Sum of the forces in the y direction is the mass times the acceleration in the y direction. So that is the Newton part, right? This part, and then we had the Euler part, and the Euler part had nothing to do with point mass. The Euler part was that suddenly we had a rigid body with extensions, with dimensions. So for the Euler part, we're going to redraw the figure, because now we say, oh yeah, in this case, again, this inertial system with the coordinates. But now we have a thing called a rigid body, and in that rigid body, remember, we have a center of mass, and that the center of mass is the point where you can think that all the mass is, you can shrink all the mass. And then suddenly we have an extra thing going on, and that is an orientation, because if you have drawn a line on the body, then the body can, of course, rotate, right? So back to 100%. Yeah, the body can rotate, meaning that with respect to the, say the x-axis, you have something called an orientation, and that is like a new coordinate, because we have a finite body. And then, how do you get the equation of motion? Well, the thing is, you just take the approach from here, and you assume that the body is built up out of a whole collection, a sum of all these point masses. They make the total body at a distance r from the center of mass, and then you just apply Newtonian laws to the sum of all these parts. This is then a dm, part of the thing, and then finally, and you write down what is the effect of all these forces and the inertia, and how does it contribute to a torque about this central mass. And if you do that, then finally you come to the Euler equation, which says the sum of the torques about the COM equals a thing we called mass moment of inertia at the COM times angular acceleration. Now, of course, you all work with that, and the definition for this mass moment of inertia, we already know, of course, that is an integral over a distance squared, right? So that's this distance r, and r is some x prime y prime, the distance relative to the center of mass. So that's this x prime squared plus y prime squared, the distance of this mass, times this piece of mass, and then we just integrate over the volume. And that was the mass moment of inertia thing. Now, what is the units? So this is kilogram, d is nothing, unitless. X is a distance and squared, so that is distance squared. So it's something with kilograms and distance squared. Okay, let's move on. So here we have 2D, now we go to a three-dimensional world. And that is actually, yeah, not so hard, right? You just draw an extra line. So you say, oh yeah, we have X, Y, and Z. And we have a point mass here, again M. And yeah, the fun is, of course, this is a flat surface, all right? Hey, your screen is flat, everything is flat, but in some way, with our eyes and our brain, we sort of reconstruct this flat image into a spatial thing. And that's the same with here. So since I foreshorten this, I make it a little bit shorter and a skewed, and this is a right angle, but these are not right angles, then our brain is smart enough to understand, oh, that's a three-dimensional thing. But it's still a flat picture of that. It's a projection, as we say. Anyway, I don't want to talk too much about it. It's a super interesting topic. How do we reconstruct the three-dimensional world from these flat images? But let's stick to dynamics. Okay, the Newton part here, which is, yeah, just an extension, right? It's again the three-dimensional, sum of the forces, sum of the forces in the y direction is mass times y double, and the sum of the forces in the z direction is mass times z double. So one extra coordinate, one extra equation. But now let's go to the rigid body part. So again, I have this extra coordinate going on. So I have my x, I have my y, and I have my z going on. And now I have some finite rigid body with a center of mass here. And then suddenly, at the in this case, what I can draw a line on the thing, but I mean there are various orientations. There's an orientation with respect to this y-axis. Maybe there's an orientation with respect to this x-axis, and maybe there's an orientation with respect to the z-axis. Suddenly it becomes a little bit more complex, like you can rotate the body in all kinds of senses. Or in other words, where we talked about one angle here, we have here an angular velocity vector, and since it's an angular velocity vector in the three-dimensional world, we have three components, and we also have some applied torque, and again three components. Whereas in this case we just had one angular velocity, right? This guy, the omega is in this case just phi dot, and the torque is just one torque applied around the z-axis here. We didn't talk about that, but there is a z-axis perpendicular, and all the torques and all the rotation about that one axis. But suddenly here the rotation can be about three axes, although that is incorrect. What I say, that's incorrect. It's a bit more complex, and we will see in a sec. So anyway, now, by the way, we're not going to see in this lecture. That's going to be next week. But for now, we're sort of happy. Yeah, with three directions, three axes, and three rotations, and then what we write down is we say, okay, we have to know what if you apply a torque, what will change in the angular velocity, right? And what is angular velocity? We have some concept on angular velocity from the two-dimensional world. So with that concept, we then write down our equation, and we get the sum of the torques. And now it's a vector suddenly, because it has three components. About the COM equals, and again we get a thing called a mass moment of inertia. I can keep the COM. Times, angular acceleration, but that's now a vector. But suddenly we get a magic term. We get some additional stuff. We get omega cross, that's a cross product, cross, and then let's use a bracket, I omega. So this is what you could say extra. If you go from 2D to 3D, suddenly you get this extra term. And some of you are probably familiar with already this thing, but this extra term will give rise to very interesting behavior of rotation of three-dimensional bodies in space. Okay, and by the way, now when we had a scalar here, suddenly we have here a 3 by 3 matrix. This guy is suddenly a thing with dimensions. Okay, that having said, how do you get these equations? And to do that, we just don't start deriving here, but we derive here. We start here. So if we know how we got the equations here, then probably we can understand how we get that there. So how did that go? So in this case now I have to make the rigid body a little bit bigger, in the two-dimensional case. I have this rigid body, I have here this center of mass, and then within that center of mass I write a body fixed coordinate system, x prime, y prime. This was x and y, this is inertial, and this is like body fixed. And then within that coordinate system, because I'm going to do everything relative with respect to the COM, I take just a piece of mass, with its location, with its x prime and y prime. And then for that piece of mass, I can write down what the accelerations are, of course in terms of the linear accelerations here and the rotation. So I find here an x double dot, I find here a y double dot, and there's no prime because I need really everything expressed in this inertial frame, right? Not in the local rotating frame. And then the way to go here is that we just say, well, we use D'Alembert's principle to find out what is the inertia terms by saying, oh, F inertia is minus m times x double dot. That's then a way. And then we can interpret it accelerations as forces. Okay, so, well, the linear part, I'm not going to talk about that. I'm going to now talk only about the rotational part. So how does that go? Well, if this is the figure, then you can also say, oh, apparently, with all the acceleration terms here, go back to 100, yeah. If I have my body here and I have my coordinates x and y and my inertial frame, I have this body here. I have here this piece of mass with the accelerations. I can also think of it like, oh, there are two inertia forces here. There's a, and since it's a small piece of mass, there's a dF in the x direction, and here there's a dF in the y direction. This was x prime, this was y prime, and this was the COM. Center of mass. And then you can imagine, oh yeah, these inertia forces are this minus mass times acceleration, but they exert a torque about the center of mass. We have here these distances, and this force at this distance has a torque in the negative direction, and this force in that distance is positive. So we can write what is the small contribution of that piece of mass, and that is then, of course, this x distance times dFi, so that's xi times dF inertia in the y direction. Oh, I didn't write inertia here. Inertia. Yeah. And yeah, I want to be clear that it's inertia. Go away, yeah. So Fy inertia, and then the other one gives a negative torque, right? Because for now we define this as positive for our rotations. So we get minus I for particle I times the dF x inertia of particle I. Okay, and that is for this small particle I, and then of course we just, by taking the whole sum, we come up. Now the next step is, of course, we need to know what these are, the dfx and dfy, but that was super simple because we already defined that here as small mass times the acceleration. So now we have to know, because the df is the minus dm times x double dot in the x, and the dfi inertia is the minus dm y double dot. Now we have to know what are the accelerations of this piece of mass. So then we draw a third figure. Yeah. Again, we have, and everything in the inertial frame, of course, right? So here we have the inertial frame. Again, our body with our center of mass, and of course you would expect the center of mass to be at the center, but I need space to draw, right? X prime, y prime. Then we had our piece of mass here, dmi. And now we want to know what are the accelerations. Well, of course we have our linear accelerations, right? So if you say the acceleration in the x direction of this particle I is, of course, and this is the center of mass c, that is the acceleration of the center of mass, like the base motion of the whole thing. But then due to the rotation we get extra terms. So what extra terms do we get? Well, if there is a rotational angular acceleration, then of course what we get, we have in this direction then an angular acceleration of an acceleration phi double dot times this distance, and this distance was the x distance, so the x distance times this angular acceleration gives us this one in the y direction. Yeah, it's super confusing. And then in this direction it's this distance, but then in the negative apparently, so we get phi double dot times y. There shouldn't be dots here, right? Dots go away. So that is due to the angular acceleration. But we also have an angular speed, right? We also have also a phi dot. And well, most of you still remember that you then have a centrifugal acceleration inward. So there is a net centrifugal acceleration here, omega squared. Oh, let's write phi dot squared. Phi dot squared times r, and then r is of course this distance. But we need the components, of course, so there's apparently a component here and then a component here. And of course the component here is just this distance times this phi dot squared. So this guy is phi dot squared times this distance, and that is the yi. And this guy is phi dot squared times this distance, and that's the xi. Okay. Yeah. What did I do? No, I mixed the x and y up, of course, right? This is not the x. The component, the projection here of this one is of course this the xi distance. Oh. And the component of this guy is of course the yi distance. Because, well, for instance, take the simple case where this is 0, and then this is of course that distance times the angle squared, and likewise here. Anyway, in the x direction now we have to sum up everything. So it's the acceleration of the base plus the acceleration due to the rotational speed and the angular acceleration. And in the x direction it's both negative, so it's minus x prime I times phi dot squared and minus y I times phi double dot. Yeah. And in the y direction we have the acceleration of the base. So apparently there's an acceleration here going on. And what do we have then? In the y direction there's a negative part with the should be a squared here. 2 should be there's a negative one with the angular speeds, right? Minus y prime I phi dot squared. And there's a positive part, this one, with the angular acceleration. And you may remember from your homework things that these guys we usually called convective terms or something like that. Anyway, now we plug this into this and into this sum, and finally what do we get? On your page. So this contribution to this inertia torque from mass I is this distance I times the df inertia in the y direction of particle y minus this direction in the y direction times the inertia force in the x direction of particle I. And then we fill in all the stuff. So we get, what do we get? We get this xi prime times, and now I have to put, of course, dm, but for now I forget that. And then I have to take in the y direction, so that's the y acceleration, so I get y double dot c minus y prime I phi dot squared plus xi prime y double dot, and then minus the one in the y direction times the x guy, right? X double dot c minus x I prime phi dot squared minus I phi double dot, and everything times dmi. Now, looking at all these contributions, the first thing you notice, of course, is that you have here a contribution xi yi, and you have here also yi xi, and the signs are different. So here I have a plus, yeah, yeah, I have a minus, sorry, yeah, not a plus. So here's a minus sign, and here's a minus times a minus, that's a plus sign. So these guys just, they go away, right? They're not there. They cancel. And then the remaining things are these two contributions. Now, why do they go away? Well, that's of course super obvious if you look at the picture, because the centrifugal, it all has to do with the centrifugal acceleration, that one is directed towards the center of mass, meaning that it will not give a contribution to the torque about the center of mass. It's always directed to that center of rotation. Okay, so therefore they go away, and then the remaining terms are, well, let's start with the first one. So, and of course for the whole part, we have to do the integral over the volume. Then the remaining part is the integral over the volume of xi prime times y double dot c dmi. And then the nice thing is that by definition this thing is zero, because the COM is defined as having that the integral of all these distances times the mass is zero, right? That's the whole definition of the center of mass. That this point is such that if you take the sum of the masses times distance, it's like this equilibrium thing, static, that it's zero. So, and since this is a constant term for the whole body, so by definition that's zero. And likewise, if you do over the volume this y prime I x double dot c, that's this guy, dmi, by definition that is zero, right? Because the COM again is defined as x prime I dmi is zero. That's how we define the center of mass. And then the remaining terms are only these two guys. So then we get that this dmi, this inertia torque of particle I is this phi double dot times this x prime I squared plus y prime I squared times dmi. And isn't it beautiful? We see already the result we're working towards. So that is then the integral of this stuff, and since this is a constant term, you can pull that out, so you get this one plus y prime squared dmi times, put a bracket around it, phi double dot, And this is now by definition this mass moment of inertia about the center of mass. Okay, that was a long way to go get back to a familiar result. Now let's go to the three-dimensional world. How does that go? Well, in the three-dimensional world it's a bit more tricky, of course. We now suddenly have three axes, x, y and z. We have some rigid body with some extension. We have a center of mass here, COM. And then on the body we have some body fixed frame, right? And x prime, y prime, z prime. This is the inertial frame, and some body fixed frame. And then actually the whole derivation is exactly the same as for the two-dimensional case, only it's now suddenly it explodes from 1 to 3. So we have here this particle, this dmi. Then of course we have this vector now of these local distances, xy prime. We have this vector of the distance at the center of mass, xc. And then by adding those two up, we can find finally the inertial position, because that is the guy we need. We need this position vector to determine what are inertia forces, what are accelerations, all expressed in this inertial frame, which is fixed. And then the basis is, of course, that you say, oh yeah, the position I can express as this position of the center of mass plus this relative position, this xi prime. And then, of course, you proceed. You say, okay, if I have the position, how do I get the speed? Well, that is not so hard. The speed of that particle, and I'm not interested in the speed, I want to have the acceleration, right? Is the speed of the COM plus the speed of this particle in its local coordinate system. Now the nice thing is that this distance, since it's a rigid body, this distance is constant. So because we have a 3D rigid body, rigid, that is the thing. We have a rigid body, meaning that this xi prime, so the coordinates within the body are constant. Although the body can float everywhere, this distance is constant. That is the characteristic of a rigid body, and I tend to have the idea that, for instance, my head is like a rigid body, meaning that my head can move in the three-dimensional space in all kinds of ways. However, if I look in my local coordinate system, and that is nose forward, sternum high up, and one of the ears to the side, that's my XYZ coordinate system, then my nose will always remain in that local coordinate system on the same position. And my nose doesn't suddenly move like this, or moves like that, or moves like this, or moves like that. I mean, it does now because I'm not really a rigid body, but if you assume I'm a rigid body, then this location with respect to that center of mass somewhere in my brain will not change. So meaning these coordinates will not change. And therefore we can write our speed, our x dot I, as, and you would have to say x dot I dot plus omega cross x dot I, but this is 0 because of this. So our speed is just there's no dot here. Oh man. So our speed is just our angular velocity cross product with the distance. Okay. Our angular velocity cross product with it. But we're still at speed level, so we have to go one level up. So let's rewrite that. So our speed is the speed of the center of mass plus this omega cross x prime I. Now the angular acceleration well, again we just put a dot on top of everything. Go away. And that's x prime I. And then of course we have to do the change of this, which is again a change in the form of this convective term, so we get omega cross x xi prime. These are then the accelerations, so we have a linear acceleration, we have an angular acceleration, you can read this as phi double dot. And we have terms which are quadratic in the speed, because you can read this as phi dot times phi dot, phi dot squared. I will not go through this, because you already imagine, oh yeah, now you can do the whole shebang. You can say, oh, I write down what my small torque is at the COM. That is the distance cross product with this small force at inertia at the COM and then of particle I. And that of course is just the mass, this dF inertia I is just this minus the x double dot of particle I times dmi. No summation, by the way. And then, oh, my clock is in the way. That's not nice. No, oh, go away. My clock is here, of course. Let's put the clock here. I will not go into that. We have a beautiful book, and everything is in the book, right? So read all about it. It's in this book. I have a very special book, by the way. Anyway, and the final result, it's like voting for the what is it, the song festival. Final result is, the equation you will get goes like this. What is the equation we get? Following equation we get, I already showed it, of course, at the COM is mass moment at the mass moments of inertias, it's certainly plural, times angular accelerations plus angular acceleration cross product with mass moment of inertia times angular speed. And we already saw that, and now we have to know, well, what is this? Well, this is a 3×3 matrix. And how is that thing defined? So it's defined like this. In a bit, usually we write it like this: IXX, YXY, IXZ. But yeah, that is sort of boring, because you already know what's going on, right? YX, YY, Y. It doesn't tell us very much. I mean, even a smart monkey can do this, right? Well, I'm not so smart, so. It's just these 9 components. And I gave them a name. But now we have to go to how are they defined. And so, for instance, the IXX is defined as the integral over the volume over distance, and that is y squared plus z squared times dm. And likewise for the y and the z. And I will repeat that again, so I will get y in the y direction, integral over the volume, and then I get z squared plus x squared dm, and then in the about the z axis I get x squared plus y squared dm. And a smart student already recognizes this from the two-dimensional case, right? This was the guy we already had, because there all the rotations were about the z-axis in the two-dimensional case. So this was the z, x, y, all rotations was about z. So this is the mass moment of inertia, and we already knew that. Okay, so these are these diagonal terms. Then what are the other terms? Well, for instance, the yxy is, and now I hope you will remember, minus integral II. After I once made a mistake, I'll never forget. Xi yi dm. So it's just the indices x times y times dm. So it's like these cross product terms. And note that if a body, for instance, is symmetric about the y-axis or symmetric about the x-axis, then the result is 0. These terms are 0. Because if it's symmetric about the xi, then you have exactly the same contributions in the one direction as the other direction, then and this will drop out. And of course, likewise, we have the other terms. Yxz is, of course, you can remember already. You can cook it up yourself. Oh, I can drop the i's, right? So stupid. Yeah. And then what was the next one? So the next one I have to show it. So this guy, that's interesting. So the ix is then minus integral yx dm. But I already had xy dm, and that's just the difference in order, and it's scalars, so that should be identical to this guy. Ergo, this guy is symmetric. That's interesting. So the mass moment of inertia matrix, in this case, is a symmetric guy. And then the last one, well, you can cook that up, right? That's this guy, yz is then minus integral yz dm. You can imagine if you have a body with a lot of symmetries that all these cross terms, they go away. So you could say for a very symmetric body, you can finally get an IC which has the form like this: yxx, yiy, and yzz, and then it's all zeros here. But it need not be a symmetric body, because what you could also have, like for instance this box. If you take a box and you just take these x's as x, y, and z, then yeah, this clearly are x's about where there's symmetry in 3 directions. So that's all these terms go away. And it's the same for my head. I have certain symmetry left and right, not so much up and down. But still, you can come up with for everybody. So for everybody, irrespective of symmetry, you can finally come up with some, no, not a prime, some way of writing this in a diagonal form. And how do you do that? Well, of course, zeros, all zeros here. How do you do that? Well, that's of course because you take this initial form, totally filled form, and you just determine what are the eigenvalues and what are the eigenvectors, and then you transform the whole thing to those eigenvalues and eigenvectors, and then you get this. So the eigenvalues of a general case are these 3 numbers, and we call these then the principal directions. Those are the eigenvectors, and if we then transform to that, we get the principal values. Okay, so these principal values, these guys. So you can always take any rigid body, for instance, where do I have an irregular rigid body? So most rigid bodies are actually very irregular. That is a strange thing. You know, maybe that's how our life is, right? Where do I have a very irregular? Most bodies have already some symmetry, and if you have some symmetry, if you have one symmetry, already two things go away. I have an irregular body here, right? I mean, how irregular can it get? So this is a very irregular body. But it does, and if you calculate all these terms, I mean, you get a totally filled matrix here. However, if you determine the eigenvalues and eigenvectors of this guy, then, oh, time's flying when you're having fun, right? If you determine those and you transform this mass moment of inertia to these eigenvectors, eigenvalues, you just end up with this nice principal values and all these zeros. And if you do that, then of course the Euler equation of motion, they break down. So if you use principal directions for your body fixed coordinate, B, try it. Then if you take that equation, that Euler equation of motion, so that's I dropped the C for now, omega dot plus omega cross I omega. That's not a nice I. My eyes are ugly. No, not my eyes, my eyes. My eyes are okay, but these eyes are ugly. So with then this I is just a, well, let's say it's a diagonal matrix. Maybe I should write it out. And you say that's A, B, and C, and all zeros here. And if you do that, and you can write down these equations of motion, and maybe due to all these zeros, they will become a little bit simpler. Well, let's not do the zeros. Let's not do the ABC. It's a bit confusing, probably. So let's just do. Let's just do as I had before: y x x, I y y, I z z, because we work with x, y, and z here. If you write it like that, then these become a little less dense equations because we have a lot of zeros. Well, how does it go then? Well, then you should say sum of the torques, of course. Then you get three equations, because that's three equations. If I write them out, the sum of the torques about this x direction is, well, since it's a diagonal, we only have y x x times omega dot in the x direction, right? The component. And I should say omega vector was omega x, omega y, omega z. And but then we have this term, and that's rather tricky to calculate that. You can do it by your head. If you just remember that this I times this omega, since it's a diagonal, that's only a scalar thing, right? So this I omega is a vector, and it just looks I x x omega x, y y omega y, z z omega z. So in your head, you only have to remember, oh, that's the three components, but then with the I in front of it. So it looks like omega cross omega, but it isn't. And then when you do the multiplication, it's really fun when you do the cross product, because the first one is the omega z times this times minus the omega y times this guy minus the omega z times this guy. And then what do you get? Then you get II minus ZZ, because the two omegas are the same, omega Y, omega Z. And likewise, in the y direction, I mean, we get totally the same, omega dot y. Again, for the second component, you have to take the last omega, this guy, times this one, so that's zx with the ix, minus this one times this guy. So minus yzz omega z omega x. And again, we see omega z omega x, yeah, for both terms. But it's one minus the other, and it was izz minus ixx. And finally, in the third direction, we get this guy, omega dot z plus. Well, you don't have to do the product because you now sort of know what's going on. This is an x, there's no x there. This is a y, there's no y there. This is a z, so there's probably no z there. Y, x. Well, if I had here y, z, then probably I have x here. And if I have zx, then probably I have y here. It's all cyclic, it's all cyclic permutation. And this is in the three-dimensional case. So, again, you can break that down. You can say, yeah, I remember one part, and there was this, right? There was this guy. There was the two-dimensional case, and that does that comply? This is the whole three-dimensional case. So you see, and I hope everybody sees that the extension from the two-dimensional case, where you had this very simple equation, sum of the torques is mass moment of inertia about the z-axis times angular acceleration. If you go to 3D, then suddenly you explode not only in the number of equations, but also in the number of terms. You suddenly get all kind of magical terms here. And I say on purpose magical. There's some lagging going on. I get okay, there's lagging going on in the thing, but I use a router. I use a cable. Can you say that? Yeah, there's lagging going on in the live stream. I'm sorry for that, but this sort of almost ends the whole show, I guess. Oh, it's really very bad now. Let me check. Let me check for a sec. Yeah, it is connected to the cable. I'm sorry, that is the problem of working from home. Okay, then we'll finish this up. I wanted to do a demonstration, and for the recording I'll do a demonstration. These terms, they result in very strange dynamics, and you can all experience that at home if you have a simple object like this. Because in this simple object you have three different axes. You have a longitudinal, lateral, and you have exactly also